All right. So just to remind you, we're now talking about the weak coupling regime of cavity QED. And that's the regime when one of the loss rates of the system dominates. It could either be cavity field decay rate or dipole decay rate, which is loss of your atom emitter into other channels other than the cavity mode. But typically, the most interesting regime that we will be focusing on is the regime where cavity field decay rate dominates over the coupling strength. And then you still have a very good emitter, very narrow line width emitter. So coupling strength is much greater than the emitter dipole decay rate. The emitter has a very narrow line width, but cavity field decay rate exceeds coupling strength, which means that once the atom or artificial atom emits a photon goes into the cavity, it leaks from the cavity mode before it has a chance of being reabsorbed by the atom, but then still all the localization of light inside of the small volume, as we'll see today, can change the properties of this radiative decay, irreversible radiative decay, and we can actually observe something called spontaneous emission rate enhancement, which is also referred to as the Purcell effect. So last time at the very end of the lecture, I very quickly went through the review of the spontaneous emission rate in free space. So this is just a summary slide, and you have derivation in the course reader, or also you can refer to other, for example, applied quantum mechanics textbook. To solve for spontaneous emission rate in free space, you still have to solve James-Cummings Hamiltonian. You have atom two-level system, you have field, but then that's a superposition of many, many different modes in free space. And you have interaction Hamiltonian, which has the same form as James-Cummings Hamiltonian, but you have to add up over all the different modes that the atom can interact with. And then to solve for the time dependent, to solve for the behavior of the system in time domain, you solve time dependent Schrödinger equation, same way as we solve for Rabi oscillation, but now you have to keep in mind that the state of the system, wave function of the atom, wave function of the atom coupled to the field, has to be expressed in terms of superposition of additional states. So atom in the excited state, 0 photons in all the mode, or atom in the ground state and that photon going into one of the possible modes with which it can interact. So it's a little bit more complicated mathematically than solution of Rabi oscillation, but it's the same idea. And when you solve this, you observe that the probability of the system of being in the excited state with 0 photons in the all the modes would basically decay exponentially with the decay constant, which is given here with gamma naught, and that depends on the square of the atomic dipole moment between the excited and ground state. Nu is transition frequency of the atom, and the rest are fundamental constants. And this is, of course, two-level system in vacuum. We'll see what happens when you put that two-level system into a material that has refractive index n, for example, uniform material. Of course, mathematically it's the same problem, or physically it's the same problem to solve, but there are some consequences of having it in a different refractive index. So this parameter is a free space spontaneous emission rate. And of course, that's related to line width of the atom. I mean, there may be some additional broadening coming from non-radiative effects, but if it's in vacuum, it's just spontaneous emission rate into various radiative channels. And people also refer to this free space spontaneous emission as Einstein's A coefficient. And for many years, and we'll discuss that a little bit later today, people thought that the spontaneous emission rate is a property of atom that cannot be changed. And we'll see that that's not really the case, that you can change it by changing the environment. Okay, so, last time I also mentioned that you don't really need to calculate these dipole moment matrix elements, mu Eg, which could be calculated as the matrix elements, or basically inner products between the wave functions corresponding to the excited and ground state and the dipole moment, but we'd never do that. I mean, if you measure spontaneous emission rate, you can also extract dipole moment for a particular atom. So now I'd like to move on a little bit further, and first see what happens when you put that same atom into a medium that is uniform but has refractive index m. So assuming that you are not affecting, atom by some presence of surfaces or other, ions in a solid, what would happen if you simply immerse that atom into something that has refractive index m? How would its spontaneous emission rate change? And then we'll see how spontaneous emission rate will change if you completely change density of optical states, if you build a resonator or you put it in a photonic crystal or you do something else. So free space spontaneous emission rate that we derived from Jaynes-Cummings Hamiltonian can also be derived from the Fermi's golden rule. And that's probably what you have seen in some quantum mechanics classes. You would obtain exactly the same result if you start with Fermi's golden rule. But of course, Fermi's golden rule has a finite range of validity. But here, assuming that we're in the range of validity of Fermi's golden rule, you would actually obtain exactly the same result for spontaneous emission rate. And if you remember Fermi's golden rule, the expression would be that decay rate between two levels would be 2 pi divided by h bar squared, and then you would have some magnitude square of the matrix element corresponding to the interaction Hamiltonian between the excited and ground state, and then density of states. This here is exactly the same thing, but rewritten in terms of our interaction Hamiltonian. So remember that our interaction Hamiltonian for the system, and that was like on the previous slide, basically has depends on h bar g, right? And then you have absorption and emission. So for us, matrix element corresponding to transition between excited and ground state would be proportional to h bar squared and magnitude of g squared, corresponding to the mode with which that transition interacts. So instead of having here as in traditional form of Fermi's golden rule, value of the matrix element between excited and ground state corresponding to the interaction Hamiltonian, you can just write h bar squared g squared. And that's what we have here. And then that one h bar squared is canceled because you have it also in the denominator. And then here we have density of states corresponding to that transition. And one extra difference is that we have a factor of 1/3 here. And the factor of 1/3 comes from the fact that only 1/3 of all modes in free space can interact with a particular dipole orientation, right? Because you can have 3 different polarizations for the electric field for any mode chosen at a particular frequency, but only 1/3 of them would interact with the dipole. And then G0 is the same maximum value of the atom field coupling parameter that we have. And D is the density of states or density of optical modes in free space, derivation for which is in the course reader in the previous part of the notes. So, another kind of more formal way of seeing that you have 1/3 here would be to, go back to the full definition of the coupling constant between the atom and the field, which also would have this cosine psi term, which comes from the alignment of the dipole to the field. And of course, it also has the other psi term that depends on the dipole alignment relative to the field maximum. But here we're talking about the plane base. So that's not an issue. But this cosine psi term, which comes from the dipole alignment relative to the polarization of the field, would look as shown at the bottom here. And if you put that back in and then average over all possible modes and all possible mode polarizations, you will have a factor of 1/3 come up front. But it's also intuitively clear that it's 1/3 because you have 3 different modes, categories of modes. If you perfectly align your dipole relative to one set of polarizations, the other 2 would be orthogonal. They would not interact at all, but you're throwing away 2/3 of the modes. So you have 1/3 as a prefactor. So here, this is written from the Fermi's golden rule, and you can basically see that if you write it in this form and plug in G0, which we know from before, and you plug in density of optical states for free space, which we also derived last time, you will obtain exactly the same result for free space spontaneous emission rate. And you may have seen that in applied quantum mechanics 222 or 223. I'm just rewriting it here and inviting you to check. We will not really rederive it from there. But the reason why I'm rewriting it as Fermi's golden rule is because from this representation, you can see that you can change spontaneous emission rate by changing coupling strength or by changing density of optical modes, okay? So if you look at this expression, of course, this is written just for free space, but if your G changes somehow or your density of optical mode changes, then spontaneous emission rate would change. Does that make sense? Okay, so now, going back to this, let's see what would happen if you put your emitter into a material that has a refractive index n, right? So or has a uniform dielectric constant, n squared times epsilon naught, okay? So that's still a uniform medium. It's not a resonator. I mean, we're not going to discuss physical challenges in, you can't just take cesium, neutral cesium atom and put it from to glass, right? It would not really work. But, you know, let's ignore all of that for a moment and just say, okay, we just carve out a tiny, you know, cave in there and we put an atom so it's not affected by the solid, but it's the same atom, right? And material has a refractive index n squared. So how would spontaneous emission rate change, and would it change at all? Right? So we can go back to our expression written from Fermi's golden rule, which says that spontaneous emission rate is 2 pi over 3 times coupling strength squared times density of optical modes squared. So of course, we have to check whether coupling strength changes or whether density of optical modes changes. So how does it change? And, you know, of course, you all know that when you have refractive index n, it's the same thing as what we discussed in the context of light line. Dispersion of photons, or omega versus k relation, would change because the speed of light changes. Speed of light now is c over n, right? So the slope for the free photon dispersion in this material would have a slope c over n. Light line would go down by n. So does G change, and does density of optical modes change? Maybe this is my question for you. If you change material from vacuum to glass, would density of optical modes change? Yeah, most likely yes, right? Because you have different dispersion. So if you go through the same calculation that we had for density of modes in free space, there is probably something there that depends on n. And of course, dispersion depends on n. So probably it will change. What about G? Well, G, if you go back to the expression that we derived, is actually given here. And you can see that G depends on 1 over square root of epsilon, right? And that's epsilon of the material where your atom is embedded. So clearly, coupling strength does depend on epsilon or n, you know, because epsilon is proportional to n squared, which means that G would be proportional to 1 over n, and G squared would be proportional to 1 over n squared. So if you write G in the material that has a refractive index n, it would scale as G naught squared divided by n squared, where G naught is the coupling strength of that atom to modes in vacuum. Okay? So G would go down by a factor of n squared. What about density of optical modes? Well, for density of optical modes, you have to repeat the calculation you did for free space. And the way you calculate modes is by basically first finding density in K space. That would not change because you still have the same separation of modes in K space. But when you're transitioning from the K space to omega space, the way you are counting modes is you take 2 concentric spheres and then you look, which are of course corresponding to the same frequency, because equifrequency surfaces are spheres in the K space. Yes, since kx squared plus ky squared plus kz squared is k squared, and omega depends on k. So now, you know, when you count all the modes, when you go back to the density in frequency space, there will be something that depends on dk per d omega. And there is also k squared, and k squared depends on omega times n, right? So there will be an extra n squared coming from dependence between k and omega. And then one more n coming from the derivative of k relative to omega. That comes from dispersion relation. So there will be an extra factor of n cubed, okay? And that's just the derivation of density of states, density of optical modes in the medium with refractive index n. So the bottom line is the density of optical modes in material with refractive index n would be n cubed times the density of optical modes in material in a vacuum, material with refractive index 1. So then going back to spontaneous emission rate, right? If you want to compare it to spontaneous emission rate in vacuum for the same atom, the first factor would go down by a factor of n squared. The second factor would go up by a factor of n cubed, which means that overall spontaneous emission rate would go up by a factor n, okay? So spontaneous emission rate for an atom if you just take it from vacuum and put it into something that has refractive index n, it would increase by a factor of n, right? So if you put it from vacuum to glass, it would increase by a factor of 1.5. And if you put it to silicon, it would increase by a factor of 3.5, right? Simply from this analysis. But it's not a very large factor because we know refractive index may go as high as 4, but still you can increase spontaneous emission rate by a factor of maybe 4. So erbium in glass would have a spontaneous emission rate which is greater by a factor of 1.5 relative to erbium in vacuum, right? Erbium atom. Any questions? Does this make sense? So this is, it's interesting. I mean, even these exercises are relatively new. I mean, this is maybe something that people realized in about 40 years ago. No, I mean, maybe 50 years ago, 1970s or so, 40 to 50 years ago. And then, they started thinking also about modification of spontaneous emission rate in kind of more sophisticated systems. But that's what we'll be doing in a moment. But let's just summarize where we stand right now, right? So in vacuum, if you have a certain spontaneous emission rate, if you put that same atom into a medium that has a refractive index n, oops, I'm sorry, just something happened. Just a moment. Zoe? Okay, I think my daughter fell, but she's okay. Okay, so now if you actually go into a different medium, right? If you change density of optical states there, then spontaneous emission rate can change even more, right? So if you go back to Fermi's golden rule and you write it as 2 pi g squared d of nu, and you can see that if you change g, you can change spontaneous emission rate, or also if you change d, you can change spontaneous emission rate. And here I'm not writing a factor of 1/3 because now we're changing medium and we're not really talking about averaging and picking only 1/3 of the modes. It could be a medium where only one mode can interact with the atom, or some different number of modes, but we're omitting that from the expression because 1/3 here basically just came from averaging in the free space. So, if you have some medium when you can completely reduce density of optical modes, minimize it, then you would also reduce spontaneous emission rate. If you can increase it, then you would increase spontaneous emission rate. Also, if you change G, you will be able to either increase or decrease spontaneous emission rate. So basically, just by looking at the Fermi's golden rule, you can see that you can either increase or decrease spontaneous emission rate and modify it dramatically relative to the free space. So now, going back to cavities, I mean, are there any questions before we move to cavities?
I have a question.
Yeah.
So will this be different for like 2D or 1D?
2D or 1D space? Yes, absolutely. Mm-hmm. Density of states would be different. Yes. So what we're doing here, we're looking into density of optical modes in 3-dimensional space. Right. So that's inside of this derivation that we went through, right? Because I mean, it was in the lecture notes last time. Here it's just quickly repeated, but this is the expression for density of optical modes in 3-dimensional free space, right? Or 3-dimensional medium with refractive index n. So if you have 1-dimensional medium or 2-dimensional medium, I mean, if you have a waveguide or you have like a slab waveguide or 1-dimensional waveguide, it would be different from this. This is basically 3-dimensional space. Okay, but that's the idea, right? By changing D, you will change spontaneous emission rate. And in fact, if you have something like a slab waveguide 2-dimensional medium, you can increase it since you're changing density of optical modes close to the cutoff. You can actually increase it by some factor 4 or 5 at most. Okay.
Okay, thanks. Mm-hmm.
Yeah. So now, we'll spend some time kind of still looking into Fermi's golden rule and seeing how cavity can change it, right? So going back to this spontaneous emission rate, again, depends on G squared, depends on density of optical modes. How does that change in the cavity, right? Is G different and is density of optical modes different? So first, let's look at the density of optical modes. Density of optical modes changes in the cavity significantly. And an easy way to see that that happens is just to go back to the definition of density of optical modes, right? So density of optical modes would be number of modes per unit frequency interval, right? So if you think about the cavity, you have some resonance, Lorentzian with a line with delta omega, right? So if you have a one mode, I mean, assuming it's non-degenerate, it would be one mode per delta omega, right? Frequency interval, but delta omega we know is full width half maximum, which you can express as central frequency divided by Q factor, okay? So, if you just look at this, simple expression for density of optical states, you can say I have one mode per delta omega, roughly, that's order of magnitude. And delta omega is omega over Q, so the density of optical modes scales as Q over omega, okay? So by increasing Q, you will be increasing density of optical modes. Of course, if this is the only mode that you have at any frequency, imagine you have a resonator that has only one single mode, then that means that you have to also normalize the density of optical modes in such a way that the integral from minus infinity to plus infinity, or 0 to plus infinity if you're just working with positive frequencies, of this density of optical modes times d omega has to be 1, right? Because that's how density is defined. When you integrate it, you'll get the total number of modes. And the right way to normalize this density is using actually this Lorentzian factor, right? You can see that on resonance, so this is the dependent of the density of optical modes is a function of nu, and nu is of course atomic frequency that you can change. But when that frequency is equal to the cavity resonance frequency, when nu is equal to omega, you can see that this density really is proportional to Q over omega, which is what we already found out from this very simple intuitive explanation of counting on the number of modes. But of course, you have to make sure that you also have the right normalization, and this density of optical modes really scales as Lorentzian. Okay? So density of optical modes scales as the Q factor. The higher the Q factor, the higher the density of optical states. And that makes sense because you are localizing that one mode into a narrower frequency region. And that's the definition of density of optical modes, like how many modes you have per unit frequency. Does that make sense? Yeah. So density scales as G. What about this factor G, coupling square? Density scales as Q. Density of optical modes scales as Q. What about the coupling factor G? If you go back to the expression that we derived when we looked at the atom field interaction in Jaynes-Cummings Hamiltonian, here is the full expression, right? So it's a maximum value, and then we have these alignment parts that depend on the alignment of the atom relative to the field maximum, and also alignment of the dipole relative to the field polarization. And assuming that you put your atom into the field maximum and align it perfectly with the field polarization, then G would be equal to this prefactor. And that depends on 1 over square root of the mode volume, right? So the more you localize the field, the higher the G. We know that. So now, assuming that you put your atom into the field maximum and aligned it with the field polarization, G is equal to this maximum value, right? So just this prefactor. And also, if you assume that you put your atom in, you basically attune atom onto resonance with the cavity mode, then nu would be equal to omega, right? So the whole thing, the density of optical modes would be equal to 2Q over omega times pi, right? Which is already something that we found from our mode counting, that is proportional to Q over omega. So density of optical modes is 2Q over omega pi for atom on resonance with the field. For atom which is positioned at the field maximum, psi is 1. Aligned atom with the polarization of the field, cosine of psi is 1. So you just have G naught. G naught is this thing here. You copy it here, and you also have 2 pi coming from Fermi's golden rule. So the product of everything is given here, right? And of course, since you have G naught squared, you will have 1 over mode volume. You have square root of the square root. So the whole spontaneous emission rate basically depends on dipole moment squared and depends on Q divided by mode volume. Okay, So this is already very, very different than free space spontaneous emission rate or spontaneous emission rate in a material with refractive index N.
It's a density of states. Are we talking about the atomic level or?
No, this is density of optical modes. Yes, this is density because it's a two-level system, right? But you have different optical modes that you can couple to that particular transition to. So it's a density of optical modes, right? Yeah.
But I guess the density of optical modes from the atom is pretty narrow.
Yeah, that is the density of, well, you have a two-level system, right, which has a fixed transition, but you have some distribution of optical modes that you can couple to. And that's, you are completely right. I mean, you are primarily going, and that's also what you've probably seen when you calculated free space spontaneous emission rate using Fermi's golden rule. You will obtain some sinc function, and then in the limit, when you just have a single transition, you're basically sampling just a single mode. I mean, it would, the sinc function would converge kind of Kronecker delta, right? Where you are sampling only single modes at single frequency. And that's true, right? I mean, it's basically exactly the same exercise. But here, you know, we're just, and here we're also sampling single frequency, right? We're assuming that our mode is exactly at the cavity frequency on resonance with the cavity, right? Nu is equal to omega. But at that frequency, the density of optical modes is proportional to Q over omega, because you're at the peak of the cavity resonance. And I'll show you results later. If you detune your mode away from the cavity resonance, then density of optical modes follows Lorentzian. It rolls off, right? So you're expecting that as you're tuning your mode across the cavity resonance, your spontaneous emission rate would follow density of optical states. It would go up and down, right?
So yeah, so basically we're trying to convolute two things. One is the very narrow atomic
atom, exactly. Yes.
And that's where sample to the broad cavity.
Exactly.
So that will follow the broad cavity.
Exactly. Because we are doing all of this for the regime where atom is much narrower than everything else, so you can assume that it has zero line width. Like the gamma is negligible relative to kappa and everything else. So your atom is basically just has zero line width, and you're moving it relative to the density of optical modes. And of course, if you move it outside of the cavity, it has nothing to couple to, right? I mean, in this case, but if you put it on cavity resonance, it has higher density of optical states. That's what this Lorentzian here tells you. Okay. So, you know, of course, now we derive this density, this spontaneous emission rate for atom in the cavity, and we see it depends on Q over mode volume. And if you compare it to free space spontaneous emission rate, it's very different, right? So this is our free space spontaneous emission rate. It's the same thing we derived before, except that here I wrote it in terms of free space wavelength instead of omega and C, right? So here in free space, there is no Q, there is no V. I mean, clearly, if I increase Q over V, for a cavity, I can increase spontaneous emission rate. So now let's just, as an exercise, take ratio between gamma and gamma naught. Spontaneous emission rate for the in the cavity and in free space, right? So if you take the ratio of these two, and I'll label it as F naught, I mean, it's basically spontaneous emission rate change or enhancement, as we'll see in a moment. The ratio of these two, you know, spontaneous emission rate in a cavity, spontaneous emission rate in free space, is basically this given here. So there is some prefactor coming from some constants. There is lambda cube, which is free space wavelength, divided by n squared, refractive index of the material that is in the cavity, right? Because that I put atom into some material that has a refractive index n, and that's the location of the field maximum, and when atom is in the cavity, and then it depends on the ratio between the Q factor and mode volume of the cavity. So this clearly can be made much, much larger than 3 or 4 refractive index of the material. I mean, you can normalize mode volume by lambda cube. If you have your mode volume, which is just 1/2 of the cubic optical wavelength, then you can clearly increase, and you have Q factor, which is million, you can increase this way over 3 or 4, right? You can actually have dramatic spontaneous emission rate enhancement. And we'll see in a moment. I mean, this is pretty much Purcell factor, but there is one extra normalization part that we will add, which depends on the natural environment of the atom. Okay? So what happens when emitter is off resonance, right? And this is related to what we just discussed with Yishuo. What would change when you detune your emitter relative to the cavity resonance? Which parameter is changing?
The density of states.
Density of states is changing, right? Because you are following this Lorentzian shape. So away from the resonance, you will be following this Lorentzian line shape, right? So that's in the density of optical modes, which means that if I take this atom and scan it across the resonance, it would have maximum spontaneous emission rate when it's on resonance with the cavity, and then it would roll off on both sides. So that's coming from the density of optical modes. Of course, we assume that it's perfectly aligned. You know, it's at the location of the field maximum, and the polarization of the atom is aligned with the field polarization, right? So those parts are not here. I assume that G is equal to G maximum, but you can add those terms as well, as we'll do in a moment. What is important to add is that, you know, here we compared spontaneous emission rate of an atom in a cavity, right? And in that cavity, I said atom is in a location where refractive index is n, but then I compare that to atom in free space, right? And there is always some natural environment for atom or artificial atom, right? If you take a cesium atom or some other atom that people use in atomic physics, it has to be in vacuum, right? So you can compare free space spontaneous emission rate gamma naught with spontaneous emission rate of that atom in the cavity, which would be gamma, right? But if I, for example, take a quantum dot, indium arsenide, gallium arsenide quantum dot, indium arsenide, gallium arsenide quantum dot is an artificial atom whose natural environment is gallium arsenide, material with refractive index n, right? So I cannot really compare gamma naught to gamma. I should compare n gamma naught to gamma, because I should compare environment with uniform refractive index n, which is a natural environment for that emitter, right? And of course, for some emitters, natural environment is vacuum, but for some of them, it's not vacuum, which is why we should just look at, divide this expression by one more n, right? Or normalize gamma, divide by gamma by n gamma naught, which is spontaneous emission rate in a material with refractive index n. Okay, and that gives you this expression here, which is something that you may have seen already. It's called Purcell factor. It gives you a spontaneous emission rate enhancement for an atom relative to its natural environment, which is given by refractive index n. And this is a maximum value of spontaneous emission rate enhancement that you can achieve in a cavity with Q factor Q and mode volume V. And you would achieve this when you put an atom into the location of the field maximum and align it with polarization and so on. So this Purcell factor was first derived classically, not from Fermi's golden rule, not from any quantum mechanical derivation by Ed Purcell in 1946. He was actually looking into antenna radiation inside of different types of resonators and derived exactly the same expression. And in Course Reader, you have a reference to that. Actually, it's not even a full paper. It's a conference abstract. It's kind of half of a column in a journal. And he derived it from really all completely classically. And that paper had been forgotten for a lot of years, for many years, for about 4 decades. And then in early 1980s, Dan Kleppner from MIT started looking into this again in the context of changes of density of optical states in Fermi's golden rule. And people for a long time, until 1980s, despite this paper by Purcell, they actually thought that spontaneous emission rate is property of emitter that cannot really be changed. And then they started discussion of that again in 1980s, kind of more from quantum mechanical perspective. And that's when this Purcell's paper was again rediscovered. And there are a lot of papers in the past 30 years, since 1980s until now, that look into spontaneous emission rate changes in various environments. And in fact, in 1980s, I believe in 1981, the first paper after Purcell paper was the paper by Kleppner, where he looked into spontaneous emission rate in one-dimensional waveguides. So looking into modifications coming from simple reduction in the dimensionality of the system. Okay, so again, that's a maximum value, right? And here we derived it from Fermi's golden rule argument. We'll see that we can also derive it from different arguments, and we'll always obtain the same results. But the idea is that spontaneous emission rate is not the property of emitter that cannot be changed. You can enhance it by putting it into a cavity, but you can equally suppress it by putting it something into like photonic band gap, where density of optical modes is very small. Okay, so maybe we make a brief break here, and then after the break, I will show you another way to see this, and then we'll quickly, probably next time, go through yet another way to see this. But what I'll do after the break is show you that you get exactly the same result from the expression for energy eigenstates for coupled atom in the cavity in the presence of losses. This is what we use to find the condition for strong coupling, but the same expression can give you Purcell factor. Okay? I'm happy to take any questions if you have them.
Is there any physical picture on the equation here? I actually don't
On
have
this equation or Purcell factor equation?
This equation, the couple emitter.
Physical picture on the equation. Yeah, I mean, I think you have to look at it differently in the weak and strong coupling regime. I mean, in the strong coupling, it's really giving you new eigenstates of the system, as we discussed last time, right? But in the weak coupling regime, it's a very different situation, and it just tells you that you can modify loss rates of the system by changing how you couple atom and the cavity, right? So it's I mean, this equation is a solution of the Hamiltonian of the system, right? So there is nothing more than that couldn't be said, other than when you have coupling between light and matter, you can have eigenstates that are coupled states of light and matter, right? But then the loss rates or the frequencies would depend on the conditions of the coupling.
Yeah.
Excuse me?
Yeah, sure. Yeah.
I actually had a quick question about Q versus V. It seems like I guess I was wondering if there's some sort of limit you reach for this enhancement.
Yeah, absolutely.
It's like-
Yeah, definitely. That's an excellent question because, and sometimes when you read papers, you can see people write, oh, Q is million, mode volume is cubic optical wavelength. You can reach spontaneous emission rate enhancement of like 10,000. And that doesn't really make any sense because Purcell factor is only valid for the weak coupling regime. As you increase your Q factor and reduce mode volume, eventually you enter the strong coupling regime. So, the limit to this expression is what the boundary for the strong coupling regime, because in the strong coupling regime, you have reversible oscillation. It's not Purcell enhancement anymore. So before making any claims about how large Purcell factor can be, people should check whether, for the maximum value that they're quoting, maybe the system is already in the strong coupling regime. And there is no, you are not really enhancing spontaneous emission rate. There is just Rabi oscillation happening with certain rate.
And can you see that transition experimentally, like to the
Yeah,
Rabi?
absolutely. You can see the transition because in the weak coupling regime, and we'll be showing experimental results today. In the weak coupling regime, as you are, if you are, for example, looking into transmission through the system, you're just seeing single resonance. There is no Rabi splitting, right? And then as you tune the system on resonance, you start seeing Rabi splitting, right? So you start seeing two peaks pop up instead of like kind of quantum dot or your atom kind of transition directly crossing the cavity and sitting on top of the cavity. So we'll show that, yeah, now. But definitely it is what we were discussing last time, right? It's kind of transition is all smooth because even in the weak coupling regime, if you're looking at the transmission through the system, if system exhibits large Purcell factor in transmission, you can see something like a dip in the cavity resonance induced by the atom. But the two sides of that, but it's really a dip induced by the atom inside of the cavity resonance. The envelope of everything is the cavity resonance. I'll show you some results today. But as you enter strong coupling regime, these two peaks start separating by G, right? So it's the properties of the peaks, although kind of it looks like some two peaks next to each other, they're very different types of peaks. They're not really new eigenstates, but instead, in the weak coupling regime is just a cavity resonance with a dip inside.
Okay, and that's different than two coupled cavities that happen to have some overlap.
Yeah, definitely, very different.
Okay.
Yes, because it's a single cavity spectrum with a dip inside in the weak coupling regime, but only when you have strong Purcell factor, right? Okay, so let's go back to business. I just said before the break that when you have an atom coupled to the cavity, spontaneous emission rate can be enhanced by Purcell factor, and maximum enhancement is given here. And of course, keep in mind that this is just a number, has no units. Purcell factor has no units because Q is unitless and mode volume is in units of lambda cube. So typically people would express mode volume, lambda cube and mode volume are in the same units, which is dimension cube, right? So if you express your mode volume, if your mode volume is equal to 1 cubic optical wavelength, which it would be around that value in photonic crystals, then your spontaneous emission rate would basically be proportional to 3Q divided by 4 pi squared. So if your Q factor is thousands, you can actually enhance it by a factor of 10 or 100. So now going back to another way to view this, I mean, so far we only derived it from the Fermi's golden rule. But if you go back to the expression for eigenstates that we derived for the system where atom is coupled to the cavity and both of them are lossy with losses of gamma and kappa, you can actually study this also in the weak coupling regime. We only looked into this in the strong coupling regime where G was greater than kappa half, right? That's what we did last time. But now let's look into the regime where kappa half, and kappa is cavity field decay rate, is greater than G, but gamma, atomic line width, is much, much smaller than everything else. And that's the same condition we made in Fermi's golden rule derivation, that atom line width is very, very narrow, right? You will see in a moment from this expression that if your atomic line width is very broad, so if you, for example, take some solid state emitter, colloidal quantum dot or molecule, which has a very, very broad line width, broader than the cavity resonance, Purcell factor expressions do not hold. And this is typical also mistake that you may see also in the scientific papers, because people kind of use Purcell factor expression without checking conditions of the validity. Purcell factor only holds when your atom is much narrower than the cavity resonance, okay? And otherwise, you'll see that you will actually have very, very different expression. So keep in mind, only if you can neglect atomic line width relative to cavity resonance, you can use that expression. And that's the same, condition we're using here, where gamma is much smaller than kappa and G, and the same condition that we used in Fermi's golden rule, where we assume that atom is kind of Dirac delta function in frequency space. So in this regime where cavity field decay rate dominates, you can, and gamma is much smaller than everything else, we can neglect gamma. Let's assume that we tune atom on resonance with the cavity, so delta is 0, right? We can always do that by some means, and of course we expect maximum interaction to happen then. So if you tune atom there, delta is 0, gamma is 0, so everything else is basically just G squared minus kappa squared over 4. But since kappa squared over 4 is larger than G squared, we can flip the sign and put I up front, okay? Because now we're in the regime where kappa squared over 4 is greater than G. So if you look at this expression, it's obviously very different from the expression that we had in the strong coupling regime, because now real part of the frequency is not changing, right? The only thing that is changing is imaginary part of the frequency. An imaginary part of the frequency is not a new eigenstate of the system, it's a decay rate, right? So if you measure transmission through the system, you're not going to see multiple peaks. Everything is, your atom is on resonance with the cavity at the frequency omega, but the decay rates are changing clearly when they're coupled, okay? So then, if this is basically the regime of weak coupling, right? Because you don't have new real part of eigenstates. And we can actually massage this expression a little bit more. We can just look at the loss rate. Loss rate is kappa half minus plus kappa squared over 4 minus G squared. And you can kind of group all the kappa half up front and everything else in the parentheses. And if you look at this expression in the regime when kappa squared over 4 is much greater than G squared, right? I mean, this is kind of the regime that we're looking in here, right? So it's not strongly coupled regime, but if kappa squared is much greater than G squared, then you can approximate the expression here under square root of 1 minus something small is the same thing as 1 minus 1 over that small thing, right? So you can rewrite the whole thing as shown at the next line, right? Again, under the assumption that the expression under square root is very close to 1. And when you go through all organizing and grouping all the expressions, you will obtain the following result, right? So this is just approximation of the expression that we had under the regime that kappa is much greater than G. So what we will obtain is that the two decay rates that correspond to minus and plus sign here would basically be approximately equal to kappa, which is cavity field decay rate, and the next one, the other one would be G squared over kappa. Okay? So there are two different decay rates. Let's just go back to what we're analyzing and remind ourselves what the meaning of this is. So we're tuning atom on cavity resonance, right? And we said atom is weakly coupled because cavity field decay rate dominates and atom has zero line width, right? Cavity resonance is broader than the atom. And this tells us that when atom is tuned on resonance with the cavity, right? Atom is coupled still to the cavity, both of them will be at the same frequency, that's omega, that's real part here. So there are two eigenstates with the same real part of frequency, right? One is atom, one is cavity, but they will decay with different rates. One will decay with the rate kappa, and the other will decay with the rate g squared over kappa, right? So what will decay with the rate kappa? Cavity, right? Because atom and cavity are there. They're not strongly coupled because when they were strongly coupled, decay rate was combination of gamma and kappa. But now, they're not coupled. They're not strongly coupled, just weakly coupled. So cavity will decay with the rate kappa and atom will decay with the rate g squared over kappa, right? So now let's see what this g squared over kappa is, right? Because we have to plug in numbers for G and for kappa to see if this matches what we concluded from Fermi's golden rule, right? Because that should be the decay rate for the atom on resonance with the cavity. So if you go back to expression for G on resonance, it's here, it's proportional to 1 over square root of the mode volume. Kappa depends on omega over 2q. You plug that everything here, 2G squared over kappa. And you can also divide it by gamma naught, spontaneous emission rate in free space, right? So if this is not leading any kind of new crazy result, the spontaneous emission rate that we found from simply decay and from that expression, which is 2G squared over kappa, right? You need an extra factor of 2 because the previous one was decay of the field and decay of the energy would have an extra factor of 2, right? Same as for the cavity. For the cavity, this is cavity field decay rate, but energy decay would be 2 kappa, right? And here I found G squared over kappa for atom, but that's just kind of field decay. Energy decay would have to have an extra factor of 2. So 2G squared over kappa is the decay rate of the atom coupled to the cavity resonance, right? And if everything is right in our analysis, then this 2G squared over kappa should be the same as spontaneous emission rate we found from Fermi's golden rule, right? Because that's the decay rate of the atom coupled to the cavity. So then if we go back and plug in what G is, it's here, and what kappa is, which is omega over 2q, and we divide it by spontaneous emission rate in free space, we obtain exactly the same expression as what we found when we were deriving Purcell factor. So in conclusion, 2G squared over kappa is giving you maximum spontaneous emission rate that you can have for an atom in the cavity. It's exactly the same as the result you derived from Fermi's golden rule. And this is also why often people use the expression 2G squared over kappa times gamma naught, free space spontaneous emission rate, as a definition of cooperativity, which is basically Purcell factor. It's exactly the same thing. If you plug in numbers, it's exactly the same thing. That makes sense?
I have one question.
Yeah.
2 slides ago, like one more slide.
One more, okay.
So we get the 2 decay rates. One is cavity decay rate kappa. One is G squared over kappa.
Yeah.
So therefore, if we increase the quality factor of the cavity, the kappa will decrease.
Yes.
So the cavity decay rate will decrease, but the Purcell enhancement will increase when we have even lossy cavity.
Yeah, because cavity spontaneous emission rate scales as Q factor over mode volume, right? So if you increase the Q factor, you will increase Purcell factor. Atom would decay faster, right? But the cavity would, you're right, cavity would decay slower. But this is also related to what we were just discussing with Jason over the break. There is a limit to that, because eventually you will get to the regime where your coupling strength is stronger than the cavity field decay rate, and then you have new eigenstates of the system. It's not Purcell regime anymore. So as you keep increasing your Q factor and kappa keeps decreasing, eventually you'll get to the regime where G is greater than kappa, right? Or G is greater than kappa over 4, and that's not described by these expressions anymore.
I see, yeah.
Yeah. Okay, great. So now just to summarize, I mean, we derived this from two different perspectives. One was deriving it from Fermi's golden rule. The other one was deriving it from the eigenstates of the system, but both of them give you the same result. Spontaneous emission rate of an atom in the cavity can be enhanced by this factor. Typically, we refer to the maximum enhancement as the Purcell factor. So that's just the pre-factor that we have here before the normalization of the field relative to the field maximum, right? And also you define Purcell factor relative to the natural environment of the atom, which is why we have n cubed, you know, an extra n in the denominator, as we were discussing. But of course, this maximum value is reached only when your atom is on the location of the field maximum, when it's aligned with the polarization. So those are, now I'm referring to all the extra factors here. So if it's at the field maximum location, if it's not at the field maximum location, then you will be degraded relative to the maximum value, you know, by something that's proportional to electric field amplitude divided by maximum squared. If its polarization is misaligned, it's also degraded. I'll show you experimental results. So if you kind of put it at the location of the field maximum, but it's orthogonal to the field polarization, it's not really going to be enhanced. And also, as we were discussing, it depends on where it is relative to the cavity resonance. And if you detune it relative to the cavity resonance, then you are also not reaching the maximum spontaneous emission rate enhancement. Okay? And I also wanted to add one extra comment that, you know, in the picture that we discussed, where it's only one cavity mode and density of optical states is 0 outside of it, that's not really what you would see in real world, because when you detune from the cavity resonance, there will always be some residual continuum of modes, unless you're in three-dimensional photonic crystal where you completely suppress modes. Okay, so if you go outside of the cavity resonance, completely at the tails of the Lorentzian, there will still be some, I mean, there will be no cavity resonance, but there'll be some residual density of optical modes that you can couple to. And that's this little factor F that I'm writing here when I'm drawing spontaneous emission rate as a function of the frequency or valent. Okay, and that's the residual kind of background spontaneous emission rate that you would observe. So final comment here, and which is what we already commented on before, is keep in mind that everything that we said so far for the weak coupling regime was the regime in which cavity field decay rate dominates. So kappa half is greater than G, but then atomic line width is very small and negligible, the smallest parameter in the system. If you have an emitter which is broad, if you have a situation where atomic line width dominates over coupling strength, right? So this is very different. So it's not that kappa half is greater than G, but gamma half is greater than G, while cavity is very, very narrow, Q factor is extremely large, Purcell factor does not hold. So when you know, I mean, even as I mentioned during the break, sometimes you can actually see papers where people take ultra high Q cavity and very broad emitter, some molecule or some colloidal quantum dot, and then they use Purcell factor to explain enhancement in the system. That expression doesn't hold, and you can obviously see that it doesn't hold, because if you go back to the expression that we used to find Purcell factor, which is at the top of this slide, if you look at this different regime where your atom, your emitter has line width broader than the cavity, you cannot really derive Purcell factor in the same way. If you look at this different regime, you will neglect the detuning on resonance, you will neglect kappa on resonance, but you will have gamma, right? So under the square root, you have G squared minus gamma squared over 4. And then in the regime when gamma is much greater than G, you can derive, by analogy with what you derived on the previous page for Purcell factor, that the decay rate would be proportional to 2G squared over gamma. Instead of kappa, you have gamma, right? It's exactly the same exercise because kappa and gamma in this expression are kind of grouped together. So if gamma is dominant, it's not 2g squared over kappa, which is Purcell factor. It's 2g squared over gamma. So in the bad emitter limit, decay rate when your emitter is in the cavity would be 2g squared over gamma. And that's not any more enhanced by a Purcell factor because there is no Q factor here at all. G squared depends on 1 over mode volume, and gamma doesn't depend on the Q factor, okay? Which tells you that in trying to improve your Q factor is not going to help you increase spontaneous emission rate if you're already in the regime when your cavity is narrower than your emitter. You better focus on reducing mode volume. Okay, so maybe for a bad emitter, you'd rather use something like a plasmonic cavity because mode volume is small and Q factor doesn't matter anyway. Does that make sense? Right? Okay, so keep in mind, this is, very similar to Purcell factor, but it's not exactly Purcell factor because there is no Q factor here.
Could you talk about in the bad emitter case, why we're trying to shift our focus to reducing the volume?
Because if you look at the decay rate that you have there, it would be 2g squared over gamma, right? So g squared depends on 1 over mode volume. Okay?
Yeah.
And gamma is just atomic line width. So nothing here depends on the Q factor.
Okay, yeah.
So if you reduce the mode volume, you will increase this rate.
Mm-hmm. Yeah.
Okay, great. So this is just a summary in the weak coupling regime, and we're mostly interested in the Purcell regime when emitter is the narrowest in the system, but cavity field decay rate dominates. You can still reach interesting regime of interaction where the spontaneous emission rate is enhanced relative to the spontaneous emission rate without the cavity, and the maximum enhancement is given by the Purcell factor and depends on the Q factor to mode volume. But of course, that's only for the emitter that's on resonance spectrally and spatially with the cavity. Okay, so now we have a little bit more time left and we can go through various experimental examples to illustrate what we've been discussing here. Okay, any questions? If not, let's move on to experimental examples. So let's go for a moment back to quantum dots, same quantum dots that we discussed last time, chunks of indium arsenide embedded in gallium arsenide. And in this case, we'll look at the different type of cavity, which is just pillars etched inside of this one-dimensional DBR stacks, right? So you have stacks of gallium arsenide, aluminum arsenide, as you had in your homework. Then you have a spacer of gallium arsenide, which is one wavelength thick in the material. And then at the center of that spacer, you have quantum dots. And then you can etch these pillars with various diameters. I mean, you want smaller diameter to reduce mode volume. Now we know that we want to have, for the weak coupling regime, high Q over V. So you want to have high Q, and you also want to have small mode volume still. But you also, in the weak coupling regime, you are not really working on Rabi oscillation. I mean, that's still the very useful regime because it tells you that you are emitting your photons faster, your emitter decays faster. And it turns out, we'll discuss that next time, that it can also improve collection efficiency for the system. So it's useful to use the cavities where you can easily collect all of those photons. They're emitted faster, right? But you also want to make sure you collect them, which is why these pillar type cavities are pretty good if you're actually using collection to a fiber, for example, as you would be doing in a single photon source. So here are some examples showing how you're changing spontaneous emission rate, right? So here is a very simple example. You have your quantum dot in the cavity. Cavity is this micropillar cavity. Cavity resonance is here at the bottom right. And you are tuning your cavity, the quantum dot. Quantum dot line width is shown at the bottom left, right? So you see quantum dot line width narrower than the cavity line width. So we're in the regime when gamma is smaller than kappa. And we want to tune that quantum dot relative to the cavity resonance and see how spontaneous emission rate would change. So as we're tuning relative to the cavity resonance, we're taking this time resolved measurements. This is done using high-speed detectors called streak camera. It doesn't really matter, but the point is that as you're changing the wavelength of the quantum dot relative to this Lorentzian, we're also doing time resolved measurements on the decay of the quantum dot and looking at the lifetime. So here, we're changing quantum dot relative to the cavity resonance, again, using temperature changes. The same thing as we were discussing last time, because wavelength of quantum dot is much more affected by small changes in temperature. So at this particular location, and a green arrow points where quantum dot is relative to the cavity resonance, lifetime is 188 picoseconds. And then we change temperature, detune quantum dot relative to the resonance. So now it's slightly more detuned, and you measure lifetime, and it's 210 picoseconds, right? And then you detune it even more, and it's 280 picoseconds, right? And you can detune it even more. But now my question is, if I plot, so this is a lifetime, right? Lifetime, spontaneous emission rate is proportional to 1 over lifetime, right? So if I plot spontaneous emission rate, which is 1 over lifetime, what shape should I observe? As I'm changing detuning, what am I changing in the expression for spontaneous emission rate? I'm not changing location of quantum dot, right? I'm only changing detuning. So if you go back to the expression here, what is changing? Is this changing? This is not changing, right? Dipole orientation is not changing, position is not changing, prefactor is not changing, Q over B is still the same. The only thing that I'm changing is spectral detuning, which affects which is basically scanning quantum dot across the density of optical states, which is Lorentzian. So if I plot Purcell factor or spontaneous emission rate, I should see Lorentzian. Do you agree? Right, so we should see a Lorentzian. And indeed, for all these measurements, if you plot spontaneous emission rate, which is 1 over lifetime, it sits on a Lorentzian. I mean, this is half Lorentzian, it's all plotted for the positive side. And on resonance, you see 188 picoseconds lifetime. Off resonance, you see a 1 nanosecond lifetime, right? You go back to, in this case, kind of free space modes, or not free space modes for material with refractive index n, which is gallium arsenide, because the density of optical modes is the same as in bulk gallium arsenide. So this is, Purcell enhancement by a factor of greater than 5, right? So you modify spontaneous emission rate by a large factor when it's on resonance relative to off resonance. And of course, you can do many different examples in different types of cavities. So now in photonic crystals, it's the same story. You have quantum dot inside of a photonic crystal cavity. On resonance, you can increase spontaneous emission rate, in this case by a factor of 10. Off resonance, it would drop to some smaller value. And then here, there's some other interesting things that I wanted to point out, which are related to orientation of the dipole. In this case, as opposed to the pillar cavity has 2 degenerate modes with orthogonal orientation. So it doesn't really matter how dipole is oriented. There is always one mode that it can couple to because of cylindrical shape and degeneracy of the modes, right? So there are 2 modes orthogonal to each other. But this cavity is not degenerate. There is only one mode with specific polarization that you can couple to. So which means that for your quantum dot, which has 2 excitonic states that are orthogonal to each other, one would be enhanced, one would be suppressed, or not enhanced as much. So that's what we see in the inset of this figure, where the one that's aligned with the cavity decays at 650 picoseconds, and the one that's not aligned decays at 3 nanoseconds. It's the same quantum dot, it's just 2 electron hole pairs, same electron hole pair inside of the same quantum dot corresponding to neutral exciton state, but 2 different degenerate states for that exciton that have different polarization. And another interesting thing in these photonic crystals is that as you go away from the cavity resonance, you are in the photonic band gap. So density of optical states is smaller than in bulk gallium arsenide because you're in the photonic band gap, which is why when you are detuned relative to the cavity resonance, you will see suppression of spontaneous emission rate by a factor of about 8, right? And that's actually more interesting than this enhancement. This enhancement here is not very large, but suppression of spontaneous emission rate relative to bulk gallium arsenide is is interesting. And this was the first measurement that was done in solid state for a single quantum emitter, which is telling you that, I mean, if you kind of go back to Fermi's golden rule expression, you know that spontaneous emission rate depends on density of optical modes. If you put your emitter into something where you have no optical modes, density of states is suppressed, you should see suppression of spontaneous emission. And indeed, you see that here by a factor of 8 relative to the same quantum dot without photonic crystal. And if you put it in a perfect three-dimensional photonic crystal, in a photonic band gap, what would happen? It would be ideally completely suppressed, right? I mean, you excite quantum dot into excited state, it would sit there forever. Of course, that never happens because there is always some background of modes or non-radiative decay of channels that you can observe, but you will see suppression relative to the decay rate without the cavity or without any structure. And suppression just means that when you put electron into the excited state, it stays there longer before it recombines. That's what suppression means, right? Enhancement means that since it has more channels to couple to after decaying to the ground state, it has more channels for the outgoing photons, it would decay faster, right? But if it has fewer channels to couple the outgoing photon, then it would sit in that excited state longer. Does that make sense?
So
okay.
Just to clarify, the emission from the quantum dot is inside the band gap.
Yes, it is inside of the band gap, but this is not a complete band gap, right? So if you remember two-dimensional photonic crystal, first it's only for one polarization where we have band gap, and it's only band gap under the light line. So it's only a band gap for modes that are propagating in photonic crystal, but there are above light lines still leaky modes that you can couple to. But density of those modes is smaller than in free space, which is why you see some decay, but it's suppressed decay.
Okay.
Yes. And of course, you can do this for a variety of other emitters. I mean, this is what would happen when you look at silicon vacancy color center in diamond cavity. I mean, you can do it for any atom or any quantum emitter in the cavity. I'm just showing you examples for solid state emitters. It's the same regime where the emitter is narrower than the cavity resonance. What is going on here is that the cavity is scanned relative to different emitter transitions. And this is so-called silicon vacancy color center in diamond, which is basically two missing carbon atoms and silicon impurity in between. So it's kind of natural trapped silicon atom inside of the diamond lattice. Again, solid state emitter may be a little bit closer to kind of atomic physics emitter because it's not millions of atoms that are forming a quantum dot, it's still a single atom. And that silicon vacancy color center has these transitions A, B, C, D. And as you're tuning cavity relative to them, you see that they light up, okay? So if the system was strongly coupled, what would you see? Would you see this lighting up or something else? What would you see?
I guess discrete.
Shifting.
Exactly, anti-crossing, right? They will never cross, they'll anti-cross. So that's what you would see. But this is weakly coupled system. So as you're tuning them on resonance with each other, you're increasing the interaction. Emitter decays faster because of Purcell enhancement. So you see more, see these brighter crossing points, but they're still crossing. And this is enhanced by a factor greater than 40. And when you measure lifetime, again, on resonance versus off resonance, you see significant enhancement, right? It's again from time resolved measurement. And then you can actually, this is what we were discussing before. I think Jason was asking a question about the boundary between strong and weak coupling regime. It's kind of a smooth boundary, right? It's not like that abruptly you are in the strong coupling regime, but because even if you are in a weak coupling regime, but strong Purcell enhancement regime, and you're measuring transmission through the cavity, you will see some changes in transmission induced by the emitter, but you're not really seeing yet clear anti-crossing. So if you measure transmission through the cavity resonance, you see Lorentzian or inverted Lorentzian, depending on where you are collecting signal. But when you tune your emitter on resonance and you measure transmission, you see this dip, or in this case, inverted dip or peak induced by the emitter. But if you look at this carefully, it's just a dip induced in cavity resonance. It's not like two new eigenstates that are popping up and splitting by some amount. So that's for diamond, and then you can also do it. I mean, this is just like a final example. This is yet another emitter, which is silicon vacancy in silicon carbide, another semiconductor. This impurity is just missing silicon atom in silicon carbide lattice, but it kind of still behaves as a trapped atom inside of the vacuum, or kind of this solid state vacuum. And this atom also has very narrow line width, as you see on the right. And then as you tune cavity resonance relative to those atom transitions, you see them lighting up. It's not anti-crossing, it's just crossing and lighting up, and it's lighting up by a factor greater than 100. And then when you look at on resonance versus off resonance, again, you see strong reduction or radiative lifetime. One important point is, if you do these measurements to prove that you really have Purcell enhancement, one measurement is not enough. You have to prove that you both have lifetime reduction and you have intensity increase. Because if you only see increase in counts, it could just be some collection efficiency effect, that your cavity, you couple better to cavity and re-radiate in one direction. If you only see reduction in lifetime, but you don't see increase in the intensity, it could be that you're non-radiatively reducing lifetime, right? So you have to make sure that both of these are happening at the same time. And here it is happening, and also you can do statistics measurements to prove that it's a single emitter, as we did in this time.
Could you,
yeah, sure. You should.
In a previous slide, if there's a strong coupling, so there's an anti-crossing, and I'm not quite sure how to draw on the diagram.
It would be, I mean, the reason why this is a little bit more complicated here is because there are multiple emitters here that cavity is crossing. But you can forget about 1, 2, 3, 4. Imagine that you only have 2, okay?
Yeah.
On the left. So what would happen is you are tuning your cavity, and like in the V coupling regime, they are just crossing, right? But in the strong coupling regime, as you get closer to each other, they would be the same thing as in the Rabi splitting, right? The curves would break, right? And then the point is that any detuning, you will always have 2 frequencies if you take slots, like in the strong coupling regime, if you take slices vertically, right? So the vertical line would also kind of curve, right? Because it's now new eigenstates that are formed. It's not anymore just your single emitter. I mean, this single emitter frequency doesn't really matter anymore, or single cavity frequency, right? So it's sort of the same, something like this, right? One branch here, and then the other branch here.
Okay.
You get it? Yeah. Okay. I was not sure if you see my cursor. Okay, so let's stop here, and then we can continue next time. We're almost at the end of this discussion. We'll go through some remaining slides and talk also about some useful things you can do in the weak coupling regime that we discussed today, which have consequences on laser operation, and kind of discuss one more thing from another perspective, how you can see Purcell factor. And then we'll move on to kind of analyzing this in the context of various types of cavities. Okay, thank you, folks. I'll see you on Tuesday, I guess.
Thank you.
Thank you.
Bye. Bye-bye.
Thank you.